Welcome back to our AP Chemistry Notes. We are finishing up our year with acids and bases and equilibrium with them. I've been referring to this section, this unit, as Ka, Kb, and buffers. We have previously well covered Ka and Kb and how that all works and the ins and outs of that. So it's time that we finally move on to discussing the buffers part of that. And again, this whole unit is nothing new. It's simply taking our skills and understanding of equilibrium and applying it to new situations, specifically situations involving acids and bases. So you're going to see a lot of similarities even still between what we've been doing and things that we have done in the past. So a lot of your life involves acids and bases. We know that there is stomach acid in your stomach. So when it's done going through my stomach before it goes into my intestines, the pancreas will squirt some base in to start neutralizing it. Often, if it neutralizes it too much, you then go basic because a little bit of acid and a lot of base leaves it still basic. We have in our blood, which is mostly water, we have carbon dioxide because that's how it gets to our lungs to exit our body. And we know carbon dioxide dissolved in water makes carbonic acid. So there must be stuff in our blood that makes it not quite so acidic as well. Otherwise, we'd start dissolving our vessels. I even know someone who, if she drinks a Coke, it will make her sick because of the amount of acid in the Coke. So where normal people would be able to drink a Coke and balance that out in their body, she just does not have that ability in her body. And it's just something to know and be aware of. So much of life then involves buffers, the point of using acid and base to neutralize each other to maintain our homeostasis. A buffer, here's our definition, is a conjugate acid-base pair where you have both the acid and the base present in reasonable concentrations. And conjugate acid-base pair is, of course, under Bronsted-Lowry definition. So the point of a buffer is that there's some acid hanging out. So if you add any base, the acid that's hanging out would react to neutralize it. But there's also some base hanging out, and so if you add any acid, the base that's just hanging around would neutralize it. So the idea is you could add acid or base after having a buffer, and it would still neutralize, greatly minimize the change in pH based on that. Okay, so that's what a buffer is. Now let's talk about this in kind of a more specific situation. So we have this buffer system, acetic acid and sodium acetate. Now first off, I want to point out, check out the arrows. This is very common for buffers. You're going to have a weak acid and you're going to have a very soluble salt, one that ionizes completely. And that's really the key. This is a one-way arrow. This equation can only produce for me sodium ions and acetate ions. There's no other choice. There's no going backwards and giving me sodium acetate. So be aware of that. We do see, though, we have those equilibrium arrows here on our acetic acid, which, as it's a weak acid, is understandable and what you should be using there. So I have in my beaker hanging out this. Notice what I did not include. I'm not including this because it was a one-way arrow. So I have some sodium hanging out of my beaker, some acetate ion, some acetic acid that's not ionized hanging out, some hydrogen ion, which would stick to water, make hydronium. I just am not showing the water, and some acetate ion there. And yes, I did say acetate ion twice. We'll come back to that thought. So I have this stuff in my beaker. If I add some hydroxide, that is, I'm adding a base, what's going to react with it? Well, I hope you're picking out that we're probably going to get the hydrogen ion reacting with it. Okay, the hydroxide would react with hydrogen ion and form water. So how would this affect the pH? Well, I'm adding base, it's going to be neutralized by an acid and it's going to form water. So the pH really should not be affected at all, because water doesn't affect the pH of things usually, assuming you're at standard conditions and things like that. Okay. What if I add some more H+? Now, there's no OH- hanging out in order for me to neutralize it with that, but I do point this out. Okay. I'm adding H+. That means that I have more of this, and here's some equilibrium arrows right there. If I add more products, what's that going to do? Yeah, that's going to shift it to the left and make more of this, which, sorry, wrong direction, which is going to take out the added H+. I'm going to use up some acetate ion to react with my extra H+, and it's going to reform acetic acid. And acetic acid in and of itself is neutral. It's when it ionizes that it becomes acidic. So how would the pH be affected here? Well, again, if I'm neutralizing the added acid, there should be no change to the pH. So that's the point of a buffer. We have a weak acid and a salt that contains its conjugate base. Okay, so here's our weak acid ionizing into our H+ and a base, a proton acceptor. So we have a salt containing the conjugate base ion. We have a weak acid. That's our buffer system. And the point is, both times we minimize or totally neutralize even the effect of adding some extra base or adding extra acid. Okay. So I also want to point this out. Notice how adding acetic acid and sodium acetate together both give off acetate ion. Okay. So what does that mean if I have a whole bunch of acetate ion around? Well, that really is like adding some more products, which will shift the equilibrium to the left and make it harder for acetic acid to ionize in the first place. Okay. So it shifts the equilibrium to the left, and that means the amount of acetic acid that ionizes would decrease. So if we're expecting it to ionize, say, 4%, and I add then in my sodium acetate, I would expect less of it to ionize, maybe 2%. Now I'm just throwing out some random numbers, but you get the idea. Do you remember what we called this when we added an ion and it reduced the amount that would dissolve or ionize, okay, specifically to ionize in our solution? I hope you remember we called it the common ion effect. Okay. So here's the good news. The buffers are nothing new. We will not learn any new skills for handling buffers. They work just like a common ion effect worked for KSP. That's all there is to it. Now, if you're sitting here and you're like, hey, we haven't discussed KSP yet, well, don't worry. Then common ion effect in KSP is going to work just like in buffers. So really knowing one's going to tell you the other. So the good news, and I've never figured out, is it better to do one before the other? It just seems like it doesn't matter. They're two sides of the same coin kind of a thing. So we have a common ion effect. That means we're going to be applying Le Chatelier's principle, which means that as this being a one-way arrow forms these ions, that is like adding product, and so it's going to force that leftward shift to make more acetic acid from the acetate ion. Okay. So it is definitely Le Chatelier's principle that tells us about the common ion effect. Why is it just the acetic acid that's affected? Hopefully you said because this is a one-way arrow. I don't have the opportunity to go back. If they were both equilibrium arrows, yes, it would like decrease this and decrease that, but this is a one-way arrow. So it can only affect this equilibrium. So if I am adding acetate ion to acetic acid, I expect acetic acid a certain pH because it's giving off H. Does that make sense? So if I'm adding acetate ion to my acetic acid, what is that going to do? Well, that's going to use up acetate ion, and that's going to use up If I increase the acetate ion, that's going to shift it left. That's going to use up the amount of H+. So if my concentration of hydrogen ion decreases, what should happen to the pH? It should go up. So when I make a buffer, I'm not going to have a buffer able to be made equal to the pH of the acid without the buffer. Putting the two together will change the pH a little. But then once I have done that, I'm going to have a buffer system which will reduce the change in pH thereafter. So just be aware of the consequences. My pH is going to increase because I have less acid, less H+, less hydrogen ion or hydronium ion roaming around, because that would be stuck to water anyway. Okay, so that's what a buffer is. Let's do an example. And we're going to prove that buffers change the pH a little. Okay, so taking a pure acid and then adding a buffer to it changes the pH. So let's prove that. So here's my pure acid. My pure acid is acetic acid, so HC2H3O2. And I'm not going to show the water. I hope you're okay with that. Going to give me hydrogen ion and acetate ion. Yep. And I'm starting with a 0.10 molar solution there, and that's a 0, and that's a 0, because again, right now I'm doing it as if it's just a pure acid. So we've actually done a calculation just like this before, but there we go. I'm going to subtract x, I'm going to add x, I'm going to add x. That is an x. Okay. And I'm going to make the assumption here, as it's a weak acid, and 10 to minus 5 says I'm probably safe doing that. So my Ka, which is concentration of H plus times concentration of C2H3O2 minus, divided by HC2H3O2. Okay, so there's my Ka. That's going to be x squared divided by 0.10 molarity equals 1.8 times 10 to the minus 5 molarity. Oh, sorry, not molarity. There's no label on that. So x is going to be equal to, and we have some fun in our calculator, 1.8 times 10 to the minus 5 times 0.1 is 1.8 times 10 to the minus 6. I'm going to square root that. And already I'm expecting something times 10 to the minus 3, because that's the way square roots go. It's just figuring out what the square root of 1.8 is in the calculator. But second square root of 1.8 times 10 to the, it's going to be a minus 6 once I multiply both sides by 0.1. And I get 1.3 times 10 to the minus 3 molarity. I've not answered the question, but I am very close, because that is the concentration of H+. The question asks, what's the pH? No big deal. pH equals negative log concentration of H+, which is negative log of that number. If I could type it in correctly, it would help. And I get, so acetic acid, pure acetic acid by itself at 0.1 molar concentration, which is much more probably than what you would find in vinegar. It's going to have a pH of 2.87. Okay, so kind of like file that away. That's the pure acetic acid. Now what I'm going to do is take the same acetic acid, but now I'm going to add some sodium acetate to it. Okay. So what difference does that make? Well, let's analyze the sodium acetate real fast. So NaC2H3O2, one-way arrow, Na plus, and C2H3O2 minus. And if I have 0.20 molarity of that, I'm going to one-way arrow and 1-to-1 ratio. I'm going to have 0.20 molarity of that and 0.20 molarity of that. Okay, so now I'm just kind of setting that information aside. I will come back to that later. Here's my acetic acid, HC2H3O2. Again, I'm going to not show water. Not wrong if you do, not wrong if you don't, but pick one way or the other. Don't try to mix the two. That does actually make you wrong on the AP test. Either show water on both sides, one is water, one is hydronium ion, or don't show it on both sides. Okay, so there's my acetic acid, two-way arrow, because it's at equilibrium, it's a weak acid. How much of this do I start with? I start with 0.10 molarity. Okay. How much of this do I start with? Still 0, but check this out. How much of this do I start with? Because I've added that soluble salt, that gives me a one-way arrow. I am starting now with 0.20 molarity there. And I'm going to subtract x there, and I'm going to add x there, and I'm going to add x there. Okay, so what do I get at equilibrium? Very interesting here. We're used to making the assumption here, and I would make the assumption statement, as always. Make the assumption that that is still approximately 0.1. Very safe assumption to do in this particular case, because I know the answer, and I know it comes out safe. This is x, and then check this out. This is 0.20 molarity plus x. Well, if the assumption worked over here, it's going to work over here as well. So what I'm going to do is simply call this 0.20 molarity. And I would, in my assumption statement, because Ka is much, much less than 0.10 molarity or 0.20 molarity, assume ... and you fill in the rest. Assume that this math is that, and this math is that. Because this makes my Ka look very different. Now, not the formula form. That still stays the same. And do write the formula. Get your points for writing the formula, please. If it ends up being a point just for writing the formula, you're going to hate yourself for not writing the formula. So write the formula. But now, when I plug in, very interesting things I'm plugging in. I'm plugging in an x times 0.20 molarity, and I'm going to divide by 0.1 molarity, and it's still equal to 1.8 times 10 to the minus 5 as my K, as my K value. Now let's simplify, because I know this reduces to 2. So x is half of that. Okay, so no big deal there. 1.8 times 10 to the minus 5 divided by 2 to solve for x. 9 times 10 to the minus 6. Well, one of these days I will figure out what setting I have wrong that keeps moving that. I just wish I knew, because I've looked. Oh well. So that's my concentration of x, which is what? Don't just leave it as concentration of x. Be sure you state on the AP test what the purpose of x was. Purpose of x was to get me that. So my pH, which I would write out as negative log concentration of H. Okay. I'm going to still just take the negative log of that number. And I see I get 5.05 as my pH. Okay, so now let's compare. Pure acetic acid on its own? No, come on. Pure acetic acid on its own is almost a 3. Add in this much salt, and it actually is a lot of salt. I mean, it's twice as much salt as acid in comparison. So it doesn't surprise me, it's a big change. I get a pH of 5. So when we make a buffer solution by adding in a salt, it really does change the pH when we're done. But the point is, now that we have it at 5, it should stay very close to 5, whether I'm adding acid or base to it. And we'll get into some more details of that later. Okay, but this is how you work a buffer situation. Instead of starting with 0 of the anion, you should be starting with some amount from your salt. So hopefully you realize, hey, this is just like we did in KSP with the common ion effect. And you're absolutely right. We just, with acids and bases, call it a buffer instead of calling it a common ion effect. Probably because two different groups of chemists at one point in time in history were working on these separately. And the one group did common ion effect and the other group did buffers, and they didn't talk to each other until it was way too late to decide, hey, let's use the same vocabulary. So We worked it just like we worked a common nine problem, or if you happen to be watching this before doing common nine effect, hey, a buffer is going to work the same as common nine effect, so now you know how to work a common nine effect. The big change is right there. You're starting with some of the anion going on right there. And you just take that into account as you do the rest of the math. Now, if you can't make the assumption here, that's going to make this really not fun when it comes to doing the quadratic equation. But again, on the test, I expect you should be able to make the assumption that you don't need to use the quadratic equation. Okay, now some good news for you. I know, wasn't that rice table fun? I know you're just absolutely thrilled with that rice table. Well, some good news. We have actually a shortcut. Thanks to these two guys, Henderson and Hasselbalch, and they're good German names, so you have to have like phlegm in your throat and sound angry when you say it, and I'm sure I'm mispronouncing it. And if anyone who speaks German's out there and wants to like explain how to actually pronounce it correctly, I would listen. But with that said, here is the Henderson-Hasselbalch equation. Check out what it tells us. It could tell us the pH if we know the pKa of the acid, and that's just taking the negative log of Ka. That's all that is, okay? Plus the log of, and this is the concentration of the salt, specifically the anion part of the salt, and that's the concentration of the acid. Now that's usually written that way for acids. If I was doing it for a base, and we could have, a base buffer system totally, it would just look this way. Instead of A, it's a B. Instead of pH, it's POH. Instead of acid, it's a base. So it looks the same. Now here's the bad news. This is not on the AP exam. So it's a great shortcut, but they don't give you the formula. So what does that mean? Well, that means, like, as I just showed you, we can certainly work a buffer system like with a rice table and a Ka expression and get your points that way. Absolutely. But it also means if you want this equation to be faster and have a shortcut, it's up to you to memorize it. So I'm not saying not to, you go for it. Go ahead and memorize it. Just be certain you're memorizing it very carefully and don't mess up where any of these pieces go, because then you're doomed. So it's a shortcut. How is it a shortcut? Well, I could have plugged in up here 0.20 molarity for my acetate ion. I could have plugged in down here 0.10 molarity for my acetic acid. I could have found the pKa in my chart in I believe it's appendix B19, or I take the Ka, 1.8 times 10 to the minus 5 times the negative log of that, and I get that, and then boom, I get my pH. So it could go that easy. Now here's the issue. This formula only works for buffers. If you know for a fact it is a buffer system because you've identified the characteristics and you're like, oh yeah, that's going to be a buffer system, then you can use this equation and you'll be able to run it through your calculator super fast and get your answer and move on. But if it's not a buffer system and you accidentally think it is a buffer system and you try to use this equation, it'll be of no use to you whatsoever. It's certainly not coincidentally give you the right answer. So just be very careful when you do that. Okay, so we're going to take the same situation and we're going to work it with the Henderson-Hasselbalch equation. And this is going to be really just a reiteration of what I just showed you on the other screen. But we will actually work it out. Okay, so I'm going to start by showing my formula. And if I have to memorize this for the test, I want to be sure I write it down and it looks correct on my paper before I get started. It also is a great way for them to know what you are up to since it's not provided on the formula chart. Okay, so pH, I don't know the pK, but I do know it's going to be the negative log of 1.8 times 10 to the minus 5. And I'm going to add to that the log of, and as I've already said, this is going to be 0.20 molarity for my salt divided by 0.10 molarity for my acid. Hey, that reduces to 2. So now I get the pH is equal to, and all I have to do is run this through my calculator. So I'm going to take the negative log, nope, that'd be the wrong button, let's try that again. Negative log, thank you, of 1.8 times 10 to the minus 5, and I'm going to add to that the log of 2. And I get, as my pH, 5.05. Imagine that. Now, do I need to prove it? So we go back, oh, look, same pH. So it totally works. And how much faster? So there's that versus all of that. So you see why it's a shortcut. The downside is it's not on your formula chart, so if you want to use it, which is a valid thing to do on the test, but if you want to use it, you have to have it memorized. The other downside is that forgot where I was going with that, sorry. So if you want to use it on the test, you have to memorize it, and it does go that fast if you put all the right numbers in. You do want to be careful. Maybe that's where I was going. You want to be careful, though, that you only apply this equation to a system that you know is a buffer. With a weak acid, weak base, in a rice table, you're good to go anyway. But with a normal weak acid, weak base, and not a buffer system, this equation would do you no good. So don't force this equation to work for anything other than what it's been meant to work for. Okay. I feel like we need to stop there and practice some buffer calculations, and then we'll come back next time and figure out what does a buffer actually do for us. Give you a hint, since it minimizes pH change, we're going to see how the pH changes when we add things without having a buffer, and then how will they change when we do add a buffer. So good luck on your practice of just using the Henderson-Hasselbalch and doing some just normal buffer system calculations, and I'll see you next time.